Let's consider again the box sitting at the top of the cliff that we saw a couple of slides ago. So if the box is pushed over the cliff, it will lose height as it falls, which means it's going to lose potential energy. But at the same time, its velocity will increase, which means it's going faster, which means it's gaining kinetic energy. So a natural question to ask is, how does the gain in kinetic energy compare to the loss in potential energy? Are they equal, or does one outweigh the other? And the remarkable answer is that they are indeed equal. And this is a statement of the law of conservation of energy. We're going to look at that in a bit more detail in a couple of videos' time. Now, remember in this example that we're assuming that air resistance is negligible, and we can deal with those situations, those more complicated situations, a little bit later. So as the box loses potential energy, it gains exactly the amount of kinetic energy. So in other words, energy is being transferred from being stored as potential energy to being stored as kinetic energy. And we're just going to represent this qualitatively, so not using numbers so much, but just as some qualitative bar charts. So first of all, energy is conserved and it can be transferred from one storage mode to another. And here's our first example of some energy bar charts for an object falling off a cliff. So you can see here in this first part that this is at the very beginning when the object is just at the top of the cliff. It may have just been nudged off. So it has maximum potential energy. This says UG, but we use the term EG here. It has maximum potential energy and it has zero kinetic energy. If we go to 1/4 of the way through its journey, its height has decreased. It's 1/4 less of what it was at the beginning. So its potential energy has decreased by 1/4 and the kinetic energy has increased by the same amount. Halfway through the journey, you've got equal potential and kinetic energy, and continuing on until we get to the moment just before it hits the ground and all of its initial potential energy has become kinetic energy. But what's really important here is that in every single one of these time steps, the sum of the potential and the kinetic energy is constant. And so I've just drawn that time step from one to the other. So in the next example, we're going to look at a situation where we have an object sitting on top of a compressed spring, and then we let go of the spring and the object flies up into the air vertically. And again here we've got a time step from one to the next, to the next, to the next. So initially we have the object at rest sitting on top of the spring, and that system has maximum potential energy and zero kinetic because it's not actually moving. Then as the spring starts to expand, the compression is less. We get to a point where 1/4 of the object's potential energy has been transferred to the kinetic energy of the object sitting on top of the spring. And as we go through, that transfer from the potential energy storage mode to the kinetic becomes complete, and then that object is now flying up vertically through the air. And through all of this, the potential energy of the spring and the kinetic energy of the object in that system of the object and the spring is constant. So in these simple examples, the potential energy has been decreasing with time and the kinetic energy has been increasing by the same amount. And this falls down to this idea of the conservation of energy. So the sum of the energies remains constant. And that, of course, is an important statement of the conservation of energy. And we are going to come back to this yet again in a couple of videos.